From golden waves of barley swaying in the wind, to the rich foam on top of a freshly poured beer in your glass, there's an invisible, high-tech journey happening in between. Most people think brewing starts in the brewhouse. In reality, the story of every great beer begins long before the mash tun, inside giant stainless steel towers where barley is transformed by water, air, heat, and precision science. Welcome to the hidden heart of beer, the malting plant. In this video, we're going to open the doors to that world. We'll follow a barley kernel from the field into cleaning machines, steep tanks, germination boxes, hot kilns, roasting drums, and finally into storage silos as finished malt. By the end, you'll understand not just what malt is, but how modern technology, sensors, and automation turn a simple grain into the engine that drives every brew. Part 1. What's inside a barley kernel? Everything starts with a single barley kernel, small, dry, and seemingly lifeless. But inside, it's a compact biochemical factory. Each grain has the embryo, the tiny living part that can grow into a new plant, the endosperm, a storage bank full of starch and protein that will feed that new plant. The aleurone layer, a ring of living cells around the endosperm that will later produce powerful enzymes. And on the outside, a protective husk, which conveniently will later act as a natural filter bed in the brewery mash tun. In raw barley, all of this potential is locked. The starch is tightly packed and inaccessible. The enzymes we need for brewing are present, but inactive. If we tried to brew with raw barley alone, we'd get poor conversion, unstable beer, and off flavors. The job of the malting process is simple to say, but complex to execute. Wake the grain up just enough to build enzymes and soften the endosperm, then stop the growth before the plant uses up the food reserves. Doing that perfectly, on hundreds of tons of grain at a time, is what makes malting both an art and a highly engineered science. Part 2. Cleaning, sorting, and modern quality control. Before any barley is allowed into the malting system, it goes through intense cleaning and grading. Raw barley arrives from farms with dust, stones, straw, weed seeds, and sometimes damaged kernels. If these went into steep tanks and germination boxes, they would cause uneven water uptake, mold growth, and inconsistent malt quality. So the first stop is a line of machines. Pre-cleaners remove coarse impurities. Aspirators blow out light dust and chaff. Sieves and rotary screens separate grains by size. De-stoners use vibration and airflow to pull heavy stones and metal fragments out of the stream. In modern maltings, this isn't just mechanical. Optical sorters equipped with high-speed cameras and sensors can scan each grain as it falls and blast out discolored or damaged kernels with tiny jets of air in milliseconds. At the same time, lab technicians and automated sample systems check moisture content, protein levels, germination capacity, and disease damage. Only plump, healthy kernels with the right protein and enzyme potential are accepted for malting. Once the barley passes all these checks, it moves into large storage silos, ready for the first true malting step, steeping. Part 3. Steeping. Waking up the grain. Steeping is where dry, sleepy barley is gently brought back to life. Grains start with about 12% moisture. By the time steeping is complete, they will hold roughly 45% water, enough for germination to begin. In big industrial maltings, steeping happens in massive cylindrical tanks, often several meters deep. Computer systems control water temperature, fill levels, airflow, and timing with high precision. The process usually alternates between wet cycles. The grain is submerged in cool water. Air rests. The water is drained and humid air flows through the grain bed. Why alternate? Because grains don't just need water, they also need oxygen. If they stayed underwater the whole time, they would suffocate and die. During the wet phases, water enters mainly through the micropyle near the embryo, spreading from the proximal to the distal end of the kernel. The embryo, scutellum, and aleuron cells hydrate first. Gradually, water penetrates deep into the endosperm. At industrial scale, maltsters monitor this using online moisture sensors in the steep outlet, temperature probes inside the grain bed, and sometimes near infrared measurements to check moisture distribution inside a representative sample of kernels. Meanwhile, bubbled air is blown through the steep water to deliver oxygen and strip out carbon dioxide produced by the waking grains. Without this oxygen supply, enzyme production later would stall. A typical steeping schedule might include 3 wet cycles and 2 air rests, lasting 26-50 hours in total, with water temperatures between 12 and 20 degrees Celsius. By the end of steeping, most kernels show chits, tiny rootlets, just starting to break through the husk. That's the signal to move them to the next stage. Germination, Part 4. Germination. Building enzymes and modifying the grain. In traditional floor maltings, steeped barley was spread on stone floors and turned with shovels. Today, most maltsters use pneumatic germination vessels, large ventilated boxes or circular salad-in boxes with perforated floors and automated turners. Here, the now moist barley spends 4 or 5 days being carefully encouraged to grow, but not too much. The hydrated embryo produces a plant hormone called gibberellic acid. This hormone signals the aleuron layer to start synthesizing key enzymes such as alpha and beta amylase, which break starch into smaller sugars, proteases, which break down storage proteins into soluble amino acids, beta-glucanases, which reduce cell wall gums and improve filtration. These enzymes slowly penetrate the endosperm, softening it and making it friable. This is called modification. A well-modified malt will later crush easily in the brewery mill and release its starch and proteins cleanly into the mash. Inside the germination vessel, a controlled flow of slightly warmed, humid air is blown up through the grain bed. Sensors track bed temperature at several depths, relative humidity and oxygen levels in the exhaust air, and sometimes CO2 concentration, which gives a real-time indication of grain respiration. Automated rakes periodically move through the barley, preventing the rootlets from matting together and keeping the bed open for airflow. The maltster wants strong enzyme development, but also wants to avoid over-germination, where the growing plant would start consuming too much of the starch we need for brewing. A classic visual indicator is the length of the acrospire, the shoot that grows inside the husk. By the end of germination, it's usually about 3/4 to the full length of the kernel. At this point, the barley is no longer just barley. It's called green malt. It's full of active enzymes, has a high moisture content, and is too fragile and unstable to store. Time to stabilize it in the kiln. Part 5. Kilning. Locking in flavor, color, and stability. Kilning is where green malt becomes shelf-stable malt. It's also where some of the first real flavor and color start to develop. Green malt is transferred to kilns, large vessels with perforated floors. Warm air is blown up through the bed in a carefully controlled schedule that can last 24-48 hours. The kilning process is often divided into stages. Free drying. At relatively low temperatures, surface and loosely bound water are removed. Forced drying. Higher air temperatures remove more tightly bound moisture and bring the malt down towards 3-5% moisture. Curing, the hottest phase, where Maillard, reactions between sugars and amino acids, create color and flavor precursors. Cooling, malt is cooled back to near ambient temperature before it is moved to storage. Modern kilns use variable speed fans to adjust airflow, heat recovery systems to reuse energy from exhaust air, and PLC-controlled temperature profiles to achieve consistent results every batch. By changing the final curing temperature and time, maltsters can create very different malt types. Low temperature kilning yields very pale, enzyme-rich Pilsner malt. Higher curing temperatures create deeper flavors and colors for pale ale, Vienna, or Munich malts. The balance is delicate, too hot for too long, and enzymes are destroyed, too cool, and the malt may taste grassy or unstable in storage. Once kilning is complete, the now dry malt is cooled, and the fragile rootlets are removed by machines. These rootlets, rich in protein and minerals, are often sold as animal feed, making malting a low-waste process. Part 6. Specialty malt technology. Caramel and roasted malts. So far, we've described base malts, the backbone of most beers. But what about the deep amber of a Märzen, the ruby glow of an Irish red ale, or the jet black foam of a stout? Those colors and intense flavors come from specialty malts, created with additional steps and higher temperatures. Caramel and crystal malts. Instead of going straight to a kiln, well-modified green malt can be transferred to a drum roaster and gently heated while still moist. The moisture and enzymes inside each kernel convert starch to simple sugars inside the grain itself. Then, as the temperature rises, those sugars caramelize. At the end of this stewing and roasting process, the inside of the kernel becomes hard, shiny, and glassy, hence the name crystal malt. Depending on time and temperature, maltsters can produce crystal malts that taste lightly sweet and toasty, richly caramel, or deeply dark, with raisin and burnt sugar notes. These malts have almost no enzyme power left, so brewers use them typically at 5–15% of the grist to add color, body, and flavor. Roasted malts. For the darkest beers, kilned malt is roasted at very high temperatures, often between 180 and 220 degrees Celsius, in drum roasters similar to coffee roasters. Short, intense roasting produces chocolate malt, with cocoa and dark toast notes. Even darker roasting produces black or roasted barley, used in stouts and porters to give profound color and flavors from coffee-like to lightly burnt. Modern roasters may include infrared burners, precise temperature control and exhaust monitoring, and cooling trays that rapidly stop the roast at exactly the right point. Part 7. Storage, automation, and the connection to brewing. Once malt is finished, it is gently conveyed to storage silos. Here, cool, dry conditions are maintained to protect flavor and enzyme activity. Automation plays a huge role at this stage. Computer systems track the origin and crop year of each lot, moisture and temperature inside silos, and even the order in which malt should be shipped to maintain first in, first out freshness. When a brewery places an order, malt is weighed, sometimes blended from different silos, to meet precise specifications, then delivered as loose, bulk malt, or in bags. In the brewhouse, the malt is crushed in a mill, mixed with hot water, and the enzymes that were carefully nurtured during germination finally go to work again, converting starch into fermentable sugars in the mash tun. Those sugars become wort. Yeast turns wort into beer. And all of it is only possible because of the meticulous work that happened earlier in the malt house. Part 8. Closing. The malting process turns raw barley from a hard, starchy seed into a flavor-packed, enzyme-rich ingredient that defines a beer's color, body, and character. Behind every glass of beer, there are not just farmers and brewers, but also maltsters, engineers, sensors, control systems, and roasting drums working in perfect coordination. So next time you raise a pint, take a second to think about that barley kernel's journey. Cleaned, sorted, steeped, germinated, kilned, roasted, tested, stored, and finally milled, all so that your beer can look, smell, and taste the way it does. Thank you for watching, and if you'd like to dive deeper into the science of brewing, don't forget to like, subscribe, and tell us in the comments which malt style you want to explore next.